The laser, a useful tool in industry, science, and medicine.
When it comes down to it, a laser is just a light with extreme focus. It's both elegantly simple and extremely complicated. And it changed the way we literally see the dimensions of our Earth, our moon, the planets, asteroids, and beyond. But it was a long road to get there. Back in the 1980s at NASA, using lasers to measure physical features from space was too experimental, too risky. Fortunately, it was also a time of change and risk-taking at Goddard Space Flight Center.
In the 1960s, there was probably not much question that when a science or applications mission came up, for the most part, it went to Goddard. And we've got to do a better job of selling ourselves and being sure that we're responsive to what headquarters is looking for in terms of the competition between ourselves and other NASA centers.
I came here as hired by the center director, Noel Hinners, in '85, and he said, so what do you want to do? I said, I want to map the topography of Mars, at this scale, not the scale of buildings. How do we do that? And he goes, well, we got folks, they do stuff. And so I met a few of them very quickly, and that was Jim Abshire, John Degnan, Jack Buffton.
We started working with laser remote sensing instrumentation. It was the same type of instrumentation that communicated from ground to satellites in satellite laser ranging. We could do a little airborne laser remote sensing, and Garvin and I sort of found each other through that. I said, come on down to Wallops and we'll fly this. And he said, oh, topography, Earth, yes, I want to measure it.
We literally took a T-39 training aircraft that was put together by the Wallops team, really impressively, and bolted in a big telescope with a laser and went flying out in northern Arizona, where I had done some field work. So out there we have Meteor Crater, we have volcanoes, and we have the Grand Canyon, and the Painted Desert. So we figured in one place we could study all this.
And it was on the strength of that Jim Garvin became interested, and it put him in a position to when Dave Smith found that his radar altimeter was canceled because it was $30 million instead of 10.
They kept talking to me about, look, we're really close to getting a laser altimeter working. And I've been in lasers actually for 20 odd years before that, if you know what I mean, but laser ranging from the ground to spacecraft. So I was very familiar with the lasers, and I wasn't averse to it, on the contrary. But NASA offered me the situation that said, look, we've got a certain amount of money for you. We're willing to spend $10 million on this instrument. But there has to be some sort of competition. You need to choose which instrument you would like to fly to measure the altimetry.
And there were 4 candidates. 3 of them are radar, and 1 the laser that we call MOLA. There was no one in their right mind that would bid a laser altimeter. Seriously. And I was all gung-ho. I was a young guy, no gray hair. There was a lot of reticence. There was so little trust that this could be done. NASA has made a monumental achievement in both radar and visible near-infrared imaging of the surfaces of Earth and other planets. But those are flat field views. And the missing dimension, the hidden dimension, which drives where energy goes, where the water flows, stability of landscapes, is the 3rd dimension. We take for granted the map. Sometimes you need the map to do what's beyond the map.
Making those maps with that crucial 3rd dimension is what laser altimetry, or LIDAR, is best at. And over the decades, Goddard's gotten pretty good at explaining just how laser altimetry works.
This is a laser altimeter, and what it does is it sends a short pulse of light
from a moving platform that's observing a surface, an airplane, a satellite.
Gets a reflection straight back off the surface.
We record that reflection and the time very precisely.
Of the pulse from the spacecraft down to the surface and back again.
Which allows us to measure the range to the surface.
When that's done repeatedly in orbit, you can build up a map.
The fast rate of light pulses and the small footprint allow LIDAR to measure with a much finer scale than traditional radars.
They had a big review, and the leading radar guy that had flown radars to Venus, Gordon Pettengill, at the end said, well, I don't know about you folks, the laser's better.
In time, Goddard would become a leader in Lidar, in mapping our Earth and planets with unprecedented precision. But for now, they had to actually build the first one.
The requirements were, of course, we were in a much higher orbit. The orbit was faster than going around the moon, so we needed a larger telescope. We needed a more sensitive detector. We needed more laser energy. So in order to put our concept together, we had to gather a team. And then we had to convince their management that this was not a crazy idea and that we actually had a realistic chance of making this happen.
We worked a lot of hours. I can remember Jim talking about, working 10-hour days, and I was doing about the same. But, it really didn't matter because it was so exciting to be working on something that was going to actually map Mars.
I was fresh out of getting my master's degree in computer engineering. I was young. I had to really dive in deep. I had to spend about 2 years working with the team on algorithms. How were we going to find the surface of Mars? How were we going to track it? How were we going to compute all the precise ranges?
And we were sort of making our way. We were defining the rules as we went.
We finished the instrument pretty much on time, and certainly as they said in the letter to me, look, if you don't make it on time and in budget, we will fly a brick instead. Okay, we're not going to hold this mission up. I knew about planetary missions; they have to go within certain windows. But anyway, we made it all right.
5, 4, 3, 2, 1. And liftoff of the Titan III rocket with the Mars Observer and America's return to the red planet. And the vehicle has cleared the tower.
We've got X-band launch at Canberra. Yeah, all right. Roger, I have that report.
Very happy crew. And Mars Observer is on its way to Mars. Trajectory is right on the money.
We've assumed that the spacecraft properly executed its orbit insertion sequence, and we presume the spacecraft is in orbit about Mars, but we have no positive confirmation of that because, as for the last 3 days, we have no communication with the spacecraft.
To say you simply don't know what happened. It could be in orbit. It could have flown past the planet.
What are the scientists doing to relieve the tension in there?
Screaming loudly, probably.
We still don't have communication with the spacecraft. However, we are very hopeful and we're cautiously optimistic that communication
Every day,
will be
in fact,
restored.
Without communications clearly lessens our probability of success.
You say, though, we give up.
We have not given up.
But I was not concerned about the spacecraft. It never crossed my mind that spacecraft would let us down. So this was a blow in the sense of, wow, something I completely didn't expect.